Welcome back, my friends, to another explainer. Picture this. It's late at night, a small, quiet room. The world outside is completely asleep. But inside, a single desk lamp is casting this warm, quiet glow. And there sits Arjun, illuminated by just the soft blue light of his monitor, his mind absolutely racing with this profound curiosity. He slowly types this exact, beautiful question right onto his screen. How does the computer actually think? Now, it feels almost philosophical, doesn't it? But the answer is purely mechanical. It's a highly choreographed dance of logic. Tonight, we're going to follow Arjun's curiosity. We're going to shrink right down, past the glowing pixels, and take a microscopic descent straight into the computer's brain. Now, to navigate this incredibly intimidating microscopic world, we're going to need a map and a very reliable guide, right? So we'll be drawing our insights from John Erickson's absolutely masterful text, Hacking: The Art of Exploitation. Erickson's work is just brilliant. Why? Because it doesn't just show you how to break things. No, it reveals the profound elegance of how things are actually built down at those lowest levels. This book is going to act as our lantern as we descend into the architecture. Okay, let's dive into this. Here is the great divide. We humans, we love high-level languages like C. They're intuitive, structured almost like cooking recipes or driving directions. But the processor inside your machine, it doesn't natively understand C or Python or any of that. It only understands machine language. It's an arcane, raw dance of ones and zeros, bits and bytes. And let me tell you, writing directly in that code is painstakingly cumbersome. So, what does this all mean? How do we actually cross this vast chasm between human logic and raw silicon? Well, we use a Rosetta Stone. We use assembly language. Assembly acts as that absolutely essential bridge. Instead of forcing a human to memorize esoteric strings of binary numbers, which is literally a nightmare, assembly uses readable mnemonics for different instructions. Yes, it's still highly specific to the physical architecture of the processor, but it takes that obscure dance of ones and zeros and translates it into manageable, precise instructions. Instructions that a curious mind like Arjun's can finally grasp. Let's zoom in a little further, past the high-level code, past the compiler. I want you to imagine a whiteboard animation unfolding right in your mind's eye. We are no longer looking at cold metal or abstract code. We have just stepped into the bustling, microscopic workspace of the x86 CPU. It's like a highly organized factory floor, and everything here has a very, very specific purpose. Looking around this mental whiteboard, the very first things we notice are the workers. Inside the CPU, these are called general-purpose registers. Think of them as these small, incredibly fast-moving workers holding temporary pieces of data exactly where the action is happening. We have EAX, the accumulator, ECX, the counter, EDX, the data register, and EBX, the base register. They are just constantly darting back and forth, holding onto a number here, passing a value over there. And these fast workers, they are absolutely crucial. Without them physically holding these temporary pieces of data, the processor literally couldn't execute its complex tasks. They act as the internal, temporary variables of the hardware itself. You see, when the CPU performs a calculation, it doesn't want to sluggishly walk all the way back to the main memory. No way. It turns to EAX or ECX standing right next to it, grabs the number, and gets the job done instantly. But my friends, out of all the incredible elements in this microscopic workspace, one demands our utmost attention. And this brilliantly illustrates the whole concept. Our guidebook describes it like this. Like a child pointing his finger at each word as he reads, the processor reads each instruction using the EIP register as its finger. The EIP, the Extended Instruction Pointer. Picture it in our whiteboard animation as a glowing, definitive finger. It is the absolute maestro of the CPU's workspace. It points to the exact, current line of code that simply must be executed right now. Now, it doesn't hold standard data like the other fast workers. Instead, it holds a memory address. It holds the precise location of the next step. Wherever the EIP points, the fast-moving workers follow. It dictates the entire flow of reality within the machine. So how does this maestro actually operate? Through a relentless, unyielding rhythm known as the execution loop. It's wonderfully structured. Step 1, the CPU reads the instruction that the EIP finger is currently pointing to. Step 2, it physically moves the finger forward, adding the byte length of the instruction to the EIP so it points to the very next command. Step 3, it actually executes the instruction it just read. And step 4, it loops right back to step 1. Read, advance, execute, repeat. Just a beautiful mechanical dance. So the crucial point we really need to understand is this. If absolutely nothing interferes, that EIP finger will just move sequentially, line by line, straight down the whiteboard. But programs aren't just straight lines, are they? We need the computer to actually make decisions. And this is where we introduce control structures, things like loops, if-then-else statements, and jumps. These structures exist for one reason, to completely change the flow of that pointing finger. Think about it. When Arjun writes a high-level logical statement, something like, "While you are hungry, eat," the compiler translates that human logic into physical, assembly-level commands. It compiles into branch, jump, and call instructions. These instructions directly command the EIP. They essentially tell that glowing finger, "Hey, stop moving downward. Jump back up to the top of the whiteboard and read that instruction again." The abstract concept of a loop is quite literally just the EIP finger being repeatedly forced back to a previous memory address. Let's move along and see how this builds. What happens when the EIP jumps away to a completely different task, like a subroutine or a function? How does it actually remember where it came from? Well, the system uses a neat structure called a stack frame. When a function is called, the CPU pushes a stack frame into memory. The absolutely most vital piece of information inside this frame is the return address. Think of it as a little sticky note left behind that says, "Hey, when you're done with this new task, jump your EIP finger exactly back to this address." It's exactly how the computer maintains context and doesn't get utterly lost. And so, as Arjun sits there watching the cursor blink in the quiet of his room, a new, slightly more dangerous realization begins to form. If the entire flow of the computer's mind is dictated by a simple finger, the EIP, reading addresses, and if those addresses are just stored in memory like anything else, how might a clever hacker exploit these control structures? How might they manipulate that stack frame to force the EIP finger to point exactly where they want it to? Well, that, my friends, is a melody for our next exploration. Until then, keep asking those profound questions.